Hi, my name is Anna Liu, and this is my lab report for lab number 2, which is the motion of a falling object. The purpose of this lab is to understand the motion of a falling object, in this case a coffee filter, and then analyze the effects of drag on said coffee filter that was dropped. And this will be done by creating two computational models, one that takes into account drag and one that does not take into account drag, and then comparing those predicted position points to the actually observed position points. First off, there are three equations that need to be understood for this experiment. The first of which is the drag equation, which is used to represent the air resistance that is being put onto the coffee filter, and this is in line with Newton's third law, which states that for every action there's an equal and opposite reaction. The next equation is the fundamental formula, which is F net equals mass times acceleration. This is also known as Newton's second law. And then this equation was used to calculate the net force that was acting on the system as it was falling. Finally, the gravity equation is used to calculate and approximate the Earth's gravity, which ended up being at around negative 9.81 meters per second. And now that we understand more about the physics, the next step was to collect the observational data points, which was done through the use of Tracker, which I will show the video for right now. In this situation, the system would be the coffee filter and the surroundings would be the air and the Earth. And to assume constant velocity for the use of this lab, only frames 195 to 238 were used, as during those frames the hand was no longer applying force to the coffee filter. And after plotting each position point by hand per frame, the data was then copied and pasted into a Google Sheets to be used for comparison, which you can see to the right. Next, to predict the data was created and collected through the usage of GlowScript and the starter code provided. As seen in the image to the right, the first code was created assuming that the only force acting on the coffee filter was gravity, and we edited the original position vector, velocity vector, range of time for the time loop, and the net force equation to fit the conditions of my lab, and this information was obtained from the tracker data points. And for the initial conditions, the ball is assumed to start at the vector of negative 0.01258 meters in the y component with an initial velocity of 0, because this is a free-falling object. And how the code works is first the code will calculate the F net of the coffee filter. However, since our system Next, the computer will then calculate the new velocity and then the new position of the coffee filter before it will loop again and start all of that over again. And it will continue doing this until our time equals approximately 1.44 seconds. And the next slide shows the code that was used to model the second computational model. And this model is almost identical to the first model, except now it also takes into account drag. And you can see that I've highlighted the drag equation that was inserted. And then also to find our B values, I guessed and checked random values of B until the output values matched my observed values the best. And once I was able to finish consolidating the data from both Tracker and GlowScript, I was able to create this graph on Google Docs or Google Sheets. And as indicated by the graph, the computational model that included the drag force was significantly more accurate than the computational model that only took into consideration the gravity. And the no drag model actually predicted that the coffee filter would fall much faster than it actually did. And this is because drag works in the opposite direction of gravity. Thus, with the inclusion of drag, the acceleration of the coffee filter was then slowed down. However, it is important to note that there was less consistency in the observed data points, and this could be due to one of two reasons. First off being human error. The observed data points were done manually by hand using Tracker's data point plotter, and thus it's unlikely that the exact center of the coffee filter was selected for every time interval. Additionally, the path of the coffee filter falling down was not entirely straight, but moved slightly from side to side. And this could be why at certain points on the graph, the predicted position was either slightly lower or slightly higher than the observed data points. And the next slide discusses the what does it mean questions, which is, do any of the models predict a terminal velocity? And the answer is yes. In both models, the drag and no drag computational model, a terminal velocity was predicted and can be seen to the graph on the right, which shows that the velocity of the coffee filter maxed out at around negative 1.4 meters per second. And at terminal velocity, the net force would be assumed to be 0, since at that point there's a constant velocity, and Newton's second law says that an object that's moving at constant velocity, that means that there are no unbalanced net forces acting upon it. And finally, we've made it to the what if slide, which is asking what if the object was thrown downwards with the initial velocity. And in my GlowScript code, I changed it so the initial velocity was -5 meters per second in the y component. And the graph on the right shows the result of the computational model, with the important part being that even with a changed initial velocity, the ultimate terminal velocity of the model remains ultimately the same, which is very interesting. As you can see, it levels back off to -1.4 meters per second. Thank you for listening.